Chapter 3 is titled Lifetime Distributions. Chapter 3 is a critical chapter in the book because everything that follows, chapters 4 through 11, all depend on a pretty thorough understanding of these lifetime distribution representations. So up until now, reliability has been considered at one particular time value. For example, the reliability of an item at time 1000 is 0.9. Now what we're going to be doing is we're going to be considering reliability as a function of time. We will not be just looking at time 1000, we'll be looking at all times and determining the reliability at any point in time. There are 5 ways that we're going to focus in on the distribution of the lifetime t, where t is some prefer to call it a positive, some prefer to call it non-negative random variable. The choice of the letter t here is because it is going to denote time. The first of the 5 is known as the survivor function, and it'll be written as s of t. The second, which is probably familiar if you've already had a first class in probability, is lowercase f of t, and that's the probability density function. The third of the 5 is the hazard function h of t, and that measures the risk that an item is subjected to at time t. The next is the cumulative hazard function, that is capital H of t. And then finally, the mean residual life function. It's given a number of names in here. We'll call it L of t. Now, we did not have to choose those 5. There are plenty of others we could have chosen. One of those others is the cumulative distribution function, which is pretty commonly used in probability. Notice that the cumulative distribution function is just the complement of the survivor function. So if you understand cumulative distribution functions, you'll have no problem picking up survivor functions. Another is the moment generating function, which is the expected value of e to the st power. Next one is the characteristic function, and that is expected value of e to the ist power. Then there is the Mellin transform, which is the expected value of t raised to the s power. There is the reversed failure rate, which is the density divided by the CDF, and it goes on and on. There's plenty of others. We have just chosen these 5 because they come up quite a bit in the literature, but the others are perfectly legitimate and certainly are covered in other reliability textbooks. So we begin with the first of the 5. The first of the 5 is a survivor function for a continuous lifetime t. And the fact that we're looking at lifetime implies that this is either a positive or a non-negative random variable. And you can see by this choice for the support here, we're choosing it to be a non-negative random variable. So the survivor function is a generalization of reliability. And here are the 2 notions. The reliability from last chapter is the probability that an item is functioning at one particular point in time. That is now going to be generalized to the survivor function, and the survivor function is the probability an item is functioning at any time t. So here is the survivor function, and it is the probability that the random variable t, which is the lifetime, is greater than or equal to t. Now this choice right here is not universal. Some people like a strictly greater than there, and some are fine with a greater than or equal to. For a continuous distribution, it doesn't matter. For a discrete distribution, whether you choose a greater than or a greater than or equal to is important. We are also going to assume that the survivor function is 1 for all negative values of t. Survivor function has a couple other names. One of those names is it is known as the reliability function, since S of t gives you the reliability at any time t. Another name that's given to the survivor function is complementary cumulative distribution function, since S of t is 1 minus f of t for continuous random variables. Now for discrete random variables, you've got to be a little more careful. One other name for the survivor function that I've seen lately out in the literature is some people will call it the survival function. So it goes by either name, survivor function or survival function. All survivor functions have to satisfy the following three existence conditions. The first condition is S of 0 is equal to 1. That is to say that the survivor function starts out at 1. So a brand new item is assumed to be an operating item and it fails at some random variable t out in the future, and S of t captures its distribution. The second says that eventually the survivor function will go to 0 as t goes to infinity. That is another way of saying eventually this item that we're looking at is going to break. And then the third existence condition is that S of t is a non-increasing function. It is not possible for the survivor function to increase at one particular point in time. There are two interpretations of S of t. One considers an individual item, and the other concerns a population. So you can think of it either way. The first interpretation is that S of t is the probability that an individual item is functioning at time t. The second interpretation is if you have a large population of items, then S of t is the expected fraction of that population which is functioning at time t. So there are two random variables in the picture below, and those two random variables are t1 and t2. These might be two different products. Maybe t1 corresponds to a light bulb from one brand, and t2 corresponds to the same wattage light bulb that has a different brand. Well, t1 is going to be governed by S1 of t, where S1 of t is its survivor function. Now that survivor function, just like all of the functions that we named earlier, a couple pages back here, all 10 of these completely define the distribution of t. So this survivor function S1 of t defines the distribution of t1 completely. S2 of t is the survivor function of the light bulb with another brand. And so the question here is, which of the two light bulbs do you prefer? Do you prefer the first brand or the second brand? Now the way you think about this is, since S1 of t is larger, then what you do is if you take any point in time, the probability of surviving here is higher for brand 1 than it is for brand 2. So if time is measured in years and this is a 1.8, the probability of surviving 1.8 years for brand 1 is higher than for brand 2. So we prefer brand 1. Now, another way of looking at that, if you look at 0.5, which is about right here on the vertical scale, and you go across, this value right here is known as the median of the distribution of the second brand, and this value right here is the median of the lifetime of the second brand. And that's another one way of saying if the median is longer, then that's going to be the preferred uh, brand of light bulb. Now, by the way, this applies to the median, which is the 50th percentile. It also applies, for example, to the 20th percentile. Here is the 20th percentile of the second brand of light bulb, and here is the 20th percentile of the first brand of light bulb. There's something known as a conditional survivor function, and that is the survivor function associated with an item which is functioning at time A. So if you notice the condition down here, we're assuming that the item has made it to time A, and we would like to have a survivor function of its remaining lifetime. That's known as a conditional survivor function. So using conditional probability, down in the denominator here, you have the probability t is greater than a. That's the condition. And in the numerator, the event is the probability t is greater than or equal to t and t is greater than a. That should be familiar from the formula. Probability of a given b is the probability of a intersect b divided by probability of b. And that's just the definition from a first probability class of conditional probability. Well, since we're only looking at t-values greater than or equal to a, this event in the numerator becomes the probability t is greater than or equal to t. And you'll notice that that is nothing more than the definition s of t. So we wind up with s of t in the numerator, and then this denominator here turns out to be s of a. So all you're doing in a sense is you're rescaling the survivor function by dividing the original survivor function by s of a, the probability of surviving to time a. Couple applications. Items surviving a burn-in test. So if you take automobile engines and let's say you run them before you place them into an automobile, let's say you run them for 10 hours and that's a burn-in test. Well, after that burn-in test is complete, if the engine passes the burn-in test and is put into an automobile, it has a conditional survivor function going forward because it's no longer a brand new engine. It has been used for 10 hours. Another is cancer patients surviving 5 years after diagnosis and treatment. So they may have a particular type of cancer, and if you look 5 years out, that's sometimes viewed in the medical profession as, in a way, being cured of the cancer. Then they have a probably much better survivor function than they originally had when the cancer was detected. Here's one that applies to life insurance premiums. Let's say you want to buy a term life insurance policy, and that is a policy which is only good for 1 year. And let's say further that you happen to purchase this policy on your 51st birthday. So obviously, if you're purchasing the life insurance policy, you're alive. And since it's only a 1-year term life insurance policy, the insurance company is very interested in knowing whether you're going to make it to age 52. Now, for most 51-year-olds, that's very, very likely that they're going to make it to age 52. The life insurance company likes that because they don't have to pay out on the life insurance policy, and you like it too because you're a year older. So everybody's a winner when a person survives to age 52, and fortunately, that probability is very high. So there's 3 applications of the conditional survivor function, and here's what they look like. Here is the survivor function of a brand new item. That could be, for example, an automobile engine. And if we burn in that automobile engine to time A, we are simply rescaling. If you remember, with the formula for the survivor function, you rescale and you get this survivor function. Now I want you to note that these have slightly different shapes. Notice this one goes into things quite gently, whereas this survivor function begins much more steeply. And that's because the used item is not as good as a new item. Sometimes they get better, sometimes they get worse, but in this particular case, a used item is not as good as a new item. The second of the lifetime distribution representations is the probability density function. This is the probability density function f of t, and it is given by the opposite of the derivative of the survivor function. Now, why is a derivative involved? Well, you know when you go from probability density function to cumulative distribution function, you integrate. So when you go in the opposite direction for a cumulative distribution function to go to a probability density function, you differentiate. The minus comes in out front because the survivor function is 1 minus the cumulative distribution function. One probabilistic interpretation, which you might or might not have seen, is if you take the probability density function and multiply it by some small time window delta t, so there's going to be a small value, then that gives you the probability of failure between t and t plus delta t. There's not much room here for a picture. Let's just draw one real quick. So if you have some probability density function, and in fact, let's start this here at time 0, and this is time, and this is f of t on this axis. If you have one time here, which we'll call t, and another time that's pretty close by, t plus delta t, because we're assuming that delta t is small, then you know that the exact value of the probability of falling between t and t plus delta t is just the area underneath the curve. But that's also close to f of t times delta t because that is this rectangular region right here. Delta t is the base of that rectangle, and the height is f of t. So as long as delta t is small, these two are pretty close, and that's why you have the approximately right there. Now, you're going to see that a little bit later interpreted for hazard functions, so kind of tuck that one away for a little while and remember it, but you'll see it in a couple slides from now. A couple notes: a graph of f of t will indicate the pattern of failure over time. In this case, in the picture that I drew here, it looks fairly bell-shaped, but not in reliability, they're not all bell-shaped. The probability of failure between times a and b is exactly this. You simply integrate from a to b. Now you remember for the survivor function there were 3 existence conditions. For a probability density function there are 2 existence conditions, and the first is that the integral from 0 to infinity of f of t dt is equal to 1. You're used to seeing this as the integral from minus infinity to positive infinity is equal to 1. However, since we only have positive support in this case because it's a lifetime, it goes from 0 to infinity. The second condition is f of t is greater than or equal to 0 for all t greater than or equal to 0. That says this function up here never dips below the horizontal axis. One last thing is to interpret the probability density function, and here is a probability density function f of t, and here is the relationship between that probability density function f of t and the cumulative distribution function capital F and the survivor function capital S. If you choose an arbitrary t0, and in this case you can see t0 has been chosen to be 1, then the area to the left of time t0 is f of t0. So this area right here is capital F of t0. The area to the right of t0 is S of t0. So this area to the right of t0 is S of t0. And that is how the probability density function f of t and the cumulative distribution function capital F of t and the survivor function all relate to one another.